All right, we'll get started as more people join in. Um, Greetings, everyone. A very warm welcome to you all to this webinar hosted by the North Central Climate Adaptation Science Center. We are based at the University of Colorado, Boulder. I am Imtiaz Rangwala, co-hosting this webinar with my colleague, Heather Yoakum. We bring you these webinars to facilitate a discussion of science, research, and best practices related to adaptation and resource management under a rapidly changing climate and other environmental changes, with a focus on the north central US that encompasses the Missouri and the upper Colorado River basins. Before I introduce our speaker, a quick word on housekeeping. We are recording this webinar, and you can find all our recordings on our website. During the webinar, all participants will be muted, but you will be able to unmute during the Q&A period at the end. We, however, encourage you to put your questions and comments in the chat anytime during the webinar, and we'll start with those questions first during the Q&A. We will end the formal part of this webinar at noon Mountain Time and stop the recording at that point. After that, anyone who wishes to engage in a more informal conversation with our speaker is encouraged to do so. And now I am pleased to introduce our speaker for today, Dr. Theo Barnhart. Theo is a research physical scientist with the U.S. Geological Survey's Wyoming, Montana Water Science Center in Helena, Montana. Theo's research focuses on future water availability in the Western United States, snow water resources, and the interactions between the mountain snowpack and streamflow. His work assists state, national, and international resource managers in understanding their water resources. Theo has a PhD in geography from the University of Colorado, Boulder. The title for today's webinar is Tongue River 2100, Future Tongue River Streamflow Estimates to Enable Northern Cheyenne Data-Driven Water Management and Planning. Thank you, Theo, for presenting to us today, and please take it away.
Thank you, Imtiaz. That was a very nice introduction. And before I get too far into this talk, I want to just, thank all of the co-authors and collaborators that are listed on the title slide here. This is very much a kind of a team science effort. So Jason Whiteman with the Northern Cheyenne Nation, Shani Spangian with the University of Idaho, Todd Blythe with the Montana Department of Natural Resources and Conservation, Megan Moore, Jay Alder, Jimmy Betzel, and Nick Taylor, all with the U.S. Geological Survey in various capacities and affiliations. And as Imtiaz said in that bio about me, this is kind of a fun presentation to give to the North Central CASC at CU Boulder, because my interest in future hydrology really started when I was a PhD student at CU. So I did my dissertation work with Noah Malich in geography and INSTAR on an NSF USDA water sustainability and climate project. And one of those chapters really focused on estimating end of century stream flow at Como Creek, which is a little catchment off of Niwot Ridge, just outside of Boulder. And I was very excited when I started the USGS to try and take what I had learned from that, kind of grad student project and apply it to a larger, more complicated watershed, which, as you'll see in this presentation, I hope the Tongue River has a lot of complexities that are more difficult perhaps than Como Creek was. So I guess this project really started, in earnest in 2022, but the the discussions around it really started, a couple years earlier than that. I think in 2019, when I first started talking with, many of the people listed on this slide about how we might put together a project like this, and build the correct relationships, and make the right connections to form a project team that would work for North Central Cask funding. So this is, really what I'm going to show you is kind of an in progress report of where we are in this project, but it's been quite a long standing effort to get it rolling and then to actually do the science work for this. So in this presentation, I'm going to talk a little bit about kind of the background of the project, who our project partners are, our scientific approach, and then I'll conclude with some preliminary results from one of our kind of subcatchments within the Tongue River watershed, and then just kind of give a little roadmap of what we have left to do as the project starts to wrap up. So if you are not in Montana or Wyoming, you might be wondering where the Tongue River is. And so the Tongue River is outlined in blue on this map, and you can see the states of Montana and Wyoming. And the Tongue River, I think, is an interesting watershed for several reasons. One is kind of its physiography. The headwaters of the Tongue are in the Bighorn Mountains, and those are quite mountainous and high elevation, with peaks above 10,000 feet. But as you can see in this map, that high elevation snow dominated portion of the watershed is a very small piece of the watershed as a whole. And that makes the watershed a bit difficult to forecast in terms of seasonal water availability studies and forecasts like what the NRCS or Natural Resources Conservation Service does. There's a large portion of the watershed that is lower elevation and more rain dominated, which leads to some of that difficulty. And then there's also many reservoirs in the watershed. There's one large reservoir just north of the Wyoming-Montana state line, which has the bulk of the storage in the basin. But then there are many smaller reservoirs perched in the Tongue River headwaters in the Bighorn Mountains that have lots of canals and irrigation ditches feeding off of them, that kind of make representing the water management in this basin a bit challenging. And I'll get into how we do that later on. And then kind of another layer of complexity or interest that I think is just kind of makes this an interesting basin to study from the human side is that this watershed is part of the Yellowstone River. It's a tributary to the Yellowstone, so it falls under the Yellowstone River Compact Commission, which essentially apportions water between the states that are part of the Yellowstone River Basin. And then there's a federal Indian water rights settlement or a water compact, I should say, between the Northern Cheyenne Nation, Montana, and the federal government. And you can see the Northern Cheyenne Reservation outlined in gray here, and the eastern boundary of the Northern Cheyenne Reservation is the Tongue River. And so the Northern Cheyenne Nation has a direct flow right in the Tongue River, as well as storage water right in the Tongue River Reservoir. And so I kind of think that this basin has a bit of an interesting geography or physiography. It has certainly a lot of interesting water management aspects, and then layered on top of all of that are the these kind of like broader scale water sharing agreements that might be important as we look at stream flow going out into the future. So with that, our project goals are really to produce and analyze future stream flow estimates in conjunction with the Northern Cheyenne Tribe and our other project partners, which I'll describe in a little bit. And when I say future streamflow estimates, that could mean a lot of things, but I kind of like to think about them in two ways, which are described in these two graphs to the right. Both of these graphs have the water year or some kind of annual metric on the horizontal axis, and the top graph has the day of water year of the peak discharge or stream flow on its vertical axis, and the bottom graph has the mean annual discharge or stream flow on its vertical axis. And so you could think about the top as kind of the timing of when stream flow is occurring at any point in the basin. This particular location is just at the Wyoming-Montana state line. And the bottom graph is kind of the amount of available water in the basin. So the blue dots here are real data from the stream gauge there. And they show that there's a lot of variability both in stream flow timing, but also in stream flow amount in this watershed. But it's not really clear if there's any real trends in this data. I've drawn some trend lines here, but they're not statistically significant. The top one is obviously very, very flat. The bottom one has a pretty wide, degree of error shading on it. But what I'm really interested in is looking out into the future, into how this, stream flow timing and amount might change going forward, and that's what these orange lines indicate as questions. And so that's kind of the knowledge gap we're hoping to fill here, and do it in a way that is useful for water resource managers in the watershed. So to do that, we're hoping to co-produce this knowledge with the Northern Cheyenne Tribe, as well as our other project partners. We need to identify locations within the watershed that are actually of real interest to the water managers. And then to actually address this knowledge gap, we need to construct and calibrate a river system model to account for all the kind of human aspects of water management in the Tongue River, like diversions and reservoir operations and crop water use and things like that. And I'll get into the methodological details later as well. So first, our project partners. We have a primary Indigenous partnership with the Northern Cheyenne citizens, as well as the Northern Cheyenne resource managers. But we also have partnerships with the Yellowstone River Compact Commission, kind of more on the water resources side, the Montana Department of Natural Resources and Conservation, as well as the Wyoming State Engineer's Office. And then because irrigation water use is such a large part of what's going on in the Tongue River, and Tongue River reservoir is so large in the watershed, we also work with the Tongue River Water Users Association, who operate Tongue River Reservoir, to understand how they're making decisions and using water. So we're working with all of these partners through kind of a partner engagement strategy, and we've done this via kind of elevational transects through the watershed, where we've made kind of 2 summer visits to the watershed and held meetings kind of going from the top to the bottom of the watershed. So we usually start out near the headwaters, meeting with the Wyoming State Engineer's Office. So this picture is taken in the headwaters of the Tongue, up in the Bighorn Mountains, at one of these kind of perched reservoirs. And so here we're learning about how the Wyoming State Engineer's Office is monitoring all the reservoirs and all the diversions. They kind of affectionately refer to this system as the mountain plumbing system, which I really like. And until you really drive around and walk around with the hydrographers that are actually working up there, it's really hard to know how complicated it really is. And you don't really see it when you're driving past the Bighorns either. So that was very interesting and very helpful to meet with them. We then kind of move downstream to just below Tongue River Reservoir, and we usually meet with the Tongue River Water Users Association. So here we're We're talking with the president of the association just below the reservoir at a nice little campground about how they're operating the dam, how the water users are calling for water, how they're when they're irrigating, how many cuttings they're doing, things like that will help us kind of inform how we should represent all the agricultural water use in the watershed in our river system model that's going to account for kind of the human side of the hydrologic cycle. And then we move down to the Northern Cheyenne Reservation, where we usually meet in the town of Bernie and the town of Ashland with Northern Cheyenne citizens and folks who are using water on the reservation to understand their questions and concerns with regard to the Tongue River. We also usually make a trip to Lame Deer, the capital of the Northern Cheyenne Reservation, to talk with the Northern Cheyenne resource managers, the tribal college. We often visit with the tribal president just to present and share what we're doing with our partners. And we have some general takeaways from this partner engagement, which has been quite helpful. When I went into this project, I kind of had this preconceived notion that drought was going to be the primary worry for many people in the watershed. And I think this kind of shows how important the partner engagement is, because it turns out that flooding is really also just as important in this watershed, particularly because there's often large rainstorms that come through, but also because of how potentially the dam is operated to move water to people needing it lower down in the river corridor. So that was very helpful to learn about, and so we've taken that information that our partners have shared with us and updated our analysis plans with ways to track how peak stream flow values and the duration of high flows might change in the future. And the primary concern around that flooding is not just people's homes and infrastructure, which is obviously very important, but also bank stability and erosion in the river corridor, which is important because if there's a lot of bank erosion, the amount of irrigable land that different irrigators have changes, and that can affect their cropping patterns or their livelihood. But also there's the pumps and the points of diversion for all this irrigation are right along the river corridor. And so, if those are undermined, that's also a very large problem. This is primarily a water quantity study. So, not all of this can we, keep in scope with the current project, but we can alter our analysis to try and address some of these concerns in terms of the types of stream flow events that might have erosion or bank stability concerns. People were also interested in testing different irrigation and planting strategies using the current water rights available, and that's kind of scenarios that we can think about putting into our river system model to see their feasibility moving forward. And then water quality is also a large concern in the watershed, particularly downstream of Tongue River Reservoir. And there's a lot of coal mining and coal bed methane development that's happened right near the Wyoming-Montana state line. And some of that has produced some very saline waters that people are concerned about. And so, water quality is sometimes linked to water quantity. And so, we can definitely speak to the quantity side of that. And, kind of knowing that that's a concern for people who are pulling the water out and putting it on their land, that's also good to know about for potential avenues for future projects in the watershed that can build off of kind of the foundation we've started here. So with, that kind of, areas of interest in mind from our project partners, we've developed a kind of a scientific approach to try and generate these future stream flow estimates throughout the watershed. And before I get into the kind of the nitty gritty of how we're doing the actual modeling, I like to start with just a diagram of the water cycle. And so, this diagram has all the kind of, stores and fluxes of where water might be on the landscape. And kind of, the middle valley of this diagram is, maybe most closely, related to the Tongue River in kind of a natural state, where there's a high mountain area that has a lot of snow, it's producing runoff. Um, but then it flows into a more lowland area where might be a lot of riparian evapotranspiration. There's certainly forest transpiration in the headwaters. But then you can see in the foreground that there are a lot of other kind of more human related water processes or hydrologic processes that are also at play here. And I'll come back to this when I kind of describe how the river system model is being constructed. But these are things like reservoir operations, evapotranspiration from crops, irrigation withdrawals, return flows, municipal and industrial water use, things like that, stock water use from grazing animals. And those are all things that we're trying to handle kind of on the river accounting model side of this project. So how are we actually getting these future stream flow estimates? And there's a lot going on in this slides, but I'll take it kind of one piece at a time. So the future hydrology that we're using for this work, which are kind of these first two diagrams, come from an already available database of future hydrology produced by Julie Vano and others. And this data set has two different future climate scenarios in it, a moderate emission scenario and a higher emission scenario from CMIP 5. Those are run through 32 different global climate models, which are then downscaled and bias corrected using the LOCA process by Pierce and others. And that uses the LIVNA meteorology data set for that downscaling and bias correction. Those downscaled and bias corrected outputs are then run through the VIC hydrologic model, which uses the same parameterization as the LIVNA data set. And so that kind of produces 64 different future streamflow or future hydrology estimates, but that doesn't account for any of the human side of the water cycle. And so what we're really doing in this project is adding that human side on and coupling that future hydrology data set to a river accounting model. And for this, we're using Riverware. And we use Riverware in kind of two different ways, which is why there are all these arrows here. We first use the river accounting model kind of in a as a way to naturalize the observed stream flow we have in the watershed. And so there's a lot of USGS and Wyoming State Engineer gauges in the Tongue River watershed that we're pulling in to do this. We first have to gap fill all those stream gauges so they have a common period of record and no missing data. We then feed those into the river accounting model that has representations of all the reservoirs and whatnot to produce a naturalized flow data set. And so that's stream flow at all the catchments we have in the watershed without any of the reservoir operations or anything like that. And we use that data to then bias correct the outputs from the future hydrology database. And then we take those bias corrected future hydrology estimates and run them back through the river accounting model, now kind of running in an operational manner with rules for the reservoirs and irrigation demand and things like that to actually produce 64 stream flow estimates throughout the watershed and accounting for kind of the human side of the hydrologic cycle. 32 of those estimates are for the moderate emission scenario. 32 of those estimates are for the higher emission scenario. And it's important that we have all these different kind of ensemble members of this future hydrology, because there are some stochastic processes and a lot of uncertainty in the global climate models. And some global climate models work better in some places than others. Some are wet, some are dry, um, things like that. And so we want to be able to show kind of the full range of variability um, to the decision makers we're working with. So in order to couple this future hydrology data set from Julie Vano to our river accounting model, we have to kind of do some spatial aggregations in the larger watershed. And so we've divided the Tongue River watershed into a series of 11 subcatchments, uh, all bounded by stream gauges. And these allow us to kind of tie the two different modeling systems together. And that brings us to the river accounting model. The Tongue River water management model is what we're calling that, but I'll use I'll call it the river system model or the river accounting model at different times in this presentation. But again, this is a model that's essentially trying to account for all the pieces of the hydrologic cycle kind of highlighted here that are usually not in a traditional hydrologic or land surface model. And so that would be like reservoir operations, irrigation, agricultural water use, return flows, stock ponds, things like that. There is kind of one larger municipality in the watershed, which is shared in Wyoming. And so there is a little bit of municipal water use and things like that as well in the basin. And when I started this project, I was perhaps a little naive in how complicated it is to build a river accounting model or this Tongue River water management model. And so it's taken quite a bit of effort and time to put this together. And this is largely the Montana Department of Natural Resources and Conservation building this model in conjunction with us. And we're getting pretty close to having it done. We have kind of draft naturalized flows that we're working with in places. And then the other parts of the model are coming together quite well. So we've done all the gap filling of the model. We've improved some aspects of the model like reservoir evaporation, agricultural water use. We've done a lot of mapping of water use, which is and digitizing of Wyoming State Engineer's Office records to kind of bring that all to fruition. And then actually creating the naturalized flows is getting quite close to being done. And kind of to give an example of what the output from this model looks like, at least in terms of naturalized flows, I have this graph at the bottom where there's time on the horizontal and then discharge or stream flow in cubic feet per second on the vertical axis. And you can see kind of the observations we have for this particular location, which is the East Fork of Big Goose Creek. And the observations we have are in red, and you can see that they're not that gauge is not functional all the time, and so we just have a little snippet of the year. But once we have done a lot of work with this river system model, we can actually produce the full naturalized flows for this location, which obviously is a bit different than the observations because we're removing reservoirs. Uh-oh, can you guys not see me anymore?
Yes, we can hear you though.
Okay. They've changed our computers, so I'm just going to leave it.
Okay,
Sorry.
sorry.
Um, but basically, this kind of shows the kind of gap filling and accounting for reservoir operations that we're trying to do throughout the whole watershed. I've alluded to this gap filling process several times. Riverware really does not like to have any missing data or different data length records, but unfortunately, not all stream gauges are operational all the time and for the same periods of record. They come and go depending on different cooperator needs. So we've started using a recursive random forest modeling technique to fill in these gaps and kind of impute the stream flow record where needed. And we constructed a little, synthetic experiment to test how well this functioned by, removing chunks of data that we actually had. And there's, and we can also feed it meteorology in the domain to, try and improve the imputation as well. And so when we have a consistent meteorology source, like back in 1976 from the LIVNA data set, the imputation is quite good. It has a Nash set-clip efficiency of 0.91. However, if we try and do it kind of a little bit earlier outside of the LIVNA data set's temporal bounds, like in 2020, the Nash set-clip declines quite a bit. And so, we're also playing with, kind of our where in the period of record we're going to do this work to make it as good as possible. I've also alluded to bias correcting the stream flow. There's an old saying that, all models are wrong, but some are useful. And so we just, we kind of take for granted that there is some error in the future hydrology data set, which, has a long historical period just for this purpose. And so we do a stream flow bias correction step to try and minimize that error and how that error might propagate into kind of subsequent pieces of our modeling chain. And to do that, we're using just a simple quantile mapping approach, which is just using the statistical properties of the naturalized flow and the future hydrology data set to try and make a correction. And this is just an example of kind of how that bias correction performs. So we've tested 4 different bias correction techniques here, and we're using kind of a 1 minus Klein-Gupta efficiency objective function for this. And you can see that the basic quantile method tends to give us a bit more, a bit higher accuracy than if we just were to use the raw flows out of the future hydrology data set. And then the graph on the right is, kind of a simplified example of what that bias correction actually looks like. So we have 3 different mean annual hydrographs shown here. So we have, the week of the water year on the horizontal axis, and then just the mean stream flow on the vertical axis for the Tongue River at Dayton, Wyoming. And the blue line is the raw data coming out of the future hydrology data set. And the red line is our naturalized stream flow for the same point, or our observations. And then the black line, it shows what the future hydrology data looks like once it's been through the bias correction process. And so it kind of, we're not expecting it to match exactly, but it does come a bit more into line with what our naturalized flow looks like. So now that I've kind of shown some of our modeling approach, I wanted to present just a few kind of preliminary results to give you guys a sense of the kinds of information that's going to come out of this project. So the next few slides focus on just one of our catchments in the watershed, the Tongue River near Dayton catchment, like I showed in the previous example. This is, a catchment in the headwaters, and it's largely free of diversions and water management, which is nice because we don't really expect these results to change a ton going forward. Before I show you the actual stream flow changes, I want to contextualize kind of what's going on, climate-wise in this catchment. So I have 4 kind of seasonal plots here: winter, spring, summer, and fall. And these show air temperature on the vertical axis, and then time on the horizontal axis. And you can see the kind of 1971 to 2000 baseline as a dashed line here. So you can see that the orange higher emission scenario is obviously getting much warmer through all these plots, and the moderated emission scenario is also getting warmer, but a little less so by the end of the century. These are the same plots essentially, but now with precipitation as the vertical axis, and we can generally see, kind of higher precipitation in both scenarios in the winter as well as the spring. The summer looks to potentially be getting a little drier going out towards the end of the century. And then the fall is about the same. And so that, kind of taking this all together, we might expect things to get slightly wetter in most seasons and generally be a bit warmer. But then, in the summer and fall, we're looking at, kind of less precipitation to maybe about the same precipitation. So how might streamflow change because of those changes? So these plots are showing the percent change in, this one shows the percent change in mean annual streamflow for the mid-century and end of century time periods for both the moderate emission scenario in blue and the high emission scenario in orange. And for mid-century, we're kind of anticipating streamflow volume decreases in anywhere from about 7 to 9%. And then by the end of century, we're anticipating kind of 9 to 17 or 18% decreases in annual volumes. The peak daily streamflow values are also changing. So these are median annual daily peak streamflow values, or changes in those values in terms of percent. Same color scheme and timing scheme as before. We're kind of anticipating a 4 to 6% decrease in peak streamflow by mid-century, and then a 7 to 15% decrease in that daily peak streamflow value by the end of century. And so this kind of describes perhaps a bit of a moderating of the hydrograph compared to the historical period. And then because we were also interested in the duration of high flows, particularly for bank stability and things like that, we've also tabulated the percent change in the number of days above the historical 95th percentile of flow. And so we also see some declines in that by mid-century, kind of a 10 to 15% decline in the number of high flow days. As well, by the end of century, we see kind of a 20 to 30% decline in the number of high flow days. And so, at least at this catchment, which keep in mind is in the headwaters, there might be a bit more moderated of an annual hydrograph. And I think it's also important to note that these are, like rolling up lots of the 32 different climate models for each scenario, and all of the years in this time period. And so that's, it's important to recognize that like it's a little bit difficult to think about like, specific events when you're doing all of that. So I just want to throw in that caveat here as well. As we, kind of work towards the end of this project, we have some planned deliverables. We're planning another swing through the watershed this coming summer to present the findings to the project partners. We're going to publish a database of this future hydrology output on the USGS Science Base, and our hope is that those data will be useful for decision makers to make analyses and decisions with, or maybe for projects for tribal college students or things like that. So that those data will be publicly available at the end of this. We're going to also build a interactive website to help people kind of explore that database, because we recognize it's going to be a lot, and so kind of offering a way to pick through some of that data in an interactive way might be very helpful. And then we're also planning a scientific paper kind of detailing our methods and results. Our next steps are really to complete the river system model. We think that's going to be done by the end of February at this point. And then we can, we've been testing all the other pieces of this system, so we think pretty rapidly bias correct our streamflow data, produce our future hydrology estimates, and then do all the analyses that we've kind of demonstrated. We're planning again these final presentations for the summer, and please, even after this presentation, reach out with any questions or input you might have. And with that, I hope we have some time for some questions and discussion.
Great. Thanks so much. Yeah, we have quite a bit of time. Thanks for a great presentation, Theo. And we see your video is back online. So it's great.
Good.
It just took a few minutes. So we have a couple questions on the chat. We'll start with those first, and then I'm just making sure that folks are able to unmute themselves and share their video anytime. So please feel free to do that. If you want to unshare your screen for a while, maybe you can do that, and then we can share it back if needed, so folks can see each other more. So, Catherine had this question around climate data, and could you say something more about the data set? I just put some links on LOCA and Giuliano's hydrology paper, but just making sure I was on the right track. And were you using CMIP5 or CMIP6? I'm guessing CMIP5.
Yeah, we used CMIP5, and at the time, well, I guess we didn't use it, but Julie Vano used it, and her group used it to produce that data set. When we were proposing and kind of having this early discussions around this project, we that data set was just coming out, and it's kind of now obviously CMIP6 has been around for a while, and it's a little bit hard to know when you're proposing something what will be available when you're ready to use it. And so that we knew that CMIP5 data set was going to be published and ready kind of by the time we got to where we could use it. So that's kind of how we made that decision. Certainly once the data set, like once the riverware model is fully done, it might be easier to slot in other future hydrology data sets as well. Or, we've had some discussions about, generating our own hydrologic model that would fit with the fabric we have. And then you could run other kinds of climate data sets through that as well.
Yeah, and before I pass it over to Ashmal, we have another question, and I'll pass it over to you after that. One comment I want to quickly make is the consensus amongst the climate scientists who are engaged in adaptation works basically is that CMIP5 is equally valid as CMIP6 to apply for all these kind of work. So, I mean, it doesn't undermine your work in any way. So the other question from Catherine is, do you have plans to compare your naturalized flows to some of the current Kona stream flow projection data set that are available? It would be interesting to see the benefit that a locally tuned management of air model provides.
We don't have a ton of plans to bring in other like stream flow projection data sets. I mean, certainly we could run we could use riverware in like just a routing model sense to essentially remove all that from like all the riverware work we've done from this to to get a sense from the LocaVic data set. Yeah, I guess I'll leave it at that.
Thanks. I'll pass it over to Ashmal. Ashmal, do you want to go ahead?
Yeah, thank you so much, Theo, for such a well-organized presentation. My name is Azmal Hossain. I'm a PhD candidate in the Department of Sociology at Colorado State University. But I work for Great Plains Tribal Water Alliance, a consortium partner of NCCASC. I have a couple of questions. Since I'm a social science background, I have like human dimensions of the project. Uh, you mentioned like you have been partnering with the Northern Cheyenne tribe. Would you please reflect a little bit? How did you develop the partnership with the Northern Cheyenne River tribe, given the like lack of trust among the tribal communities on Western hydrology, specifically if we want to focus specifically on the quantification of tribal water rights in the river basin?
Thank you for that question and your remarks. Well, I would say one, we're not focusing on the quantification of any water rights in this. The USGS provides science only, and so we kind of stay out of the water rights side of things. However, I do recognize that that's one of the reasons why this is an interesting basin to work in. In terms of relationship development, the Wyoming Montana Water Science Center, kind of the sub organization of the USGS that I work for, in some shape or form has been working with the Northern Cheyenne Tribe. Oh, I mean, probably since the 80s or earlier. We have these long-standing relationships with many cooperators, in our kind of in Montana and in Wyoming. And so when I was interested in this watershed, I was able to, kind of get an introduction to Jason Whiteman, who's the natural resources administrator for the Northern Cheyenne Tribe, from a colleague in my office. And we had phone calls and, Teams meetings and things like that. And that, it took a couple of years of just talking and kind of going through ideas, and trying to be opportunistic about what funding might be available and things like that. But that, I would say, that's how I kind of developed that relationship. And then, um, you know, we also, like, through the proposal process, it was very clear that, um, you know, trying to do good outreach with our partners and engagement with the project partners was very important. Um, so the North Central CASC, like the USGS side of it, had hired a postdoc, so at Megan Moore at the time, to kind of help with that. And they had a suite of water related projects. So Megan also helped a lot with kind of getting our presentations and things and questions honed for our discussions, with Northern Cheyenne citizens and resource managers and the tribal college. And then as part of the proposal, I I'm trying to remember how I actually met her, but Shani Spangion, who's now a professor at the University of Idaho and one of the collaborators on this project. I got in touch with her to see if she would be interested in kind of being the engagement specialist for the project. And so that's been extremely helpful. I'm not from Montana, so Montana has a program for its public schools called Indian Education for All, and so I didn't get that where I grew up, and so Shani kind of gave our project team a crash course, in some of the history, and helped us really learn, I think, how to try and do our science engagement well when we're meeting with tribal citizens and uh, officials and things like that. So I guess that's kind of a long-winded way of saying that I was maybe perhaps very fortunate to get an introduction with Jason on this project, and then kind of from that, uh, things kind of built out from there.
That's great. Thanks for that input. The other question we have is from Mary. It looks like she's left, but the question is really about relating your work to kind of near-term time horizon uh, information. So, like, do you have any thoughts about communicating your graph that currently show mid-century and end-century data points by providing a scenario planning process that allows participants to connect narratively to their past and experience and present concerns?
Yeah, that's an interesting question. And obviously the graphs I showed are pretty highly simplified. And even really leaving off like exactly what years we're looking at and things like that. And obviously there's a lot of statistical summarization going on in those graphs. But I think for moving forward, we're hoping to spend a bit more time in kind of developing these analyses, and I could see trying to match certain events to like what's shown in the hydrograph that people might remember, or things like that could be useful. Certainly we're hoping to make this data useful for people, and I think it can be a bit difficult to imagine what the future might look like given the large uncertainty bars and things like that.
Other questions? A question from Caitlin. I'm curious if you and your team put any thought on how the products of this work might be designed to help future users, recognizing that there are many different interests from ag to tribal.
Yeah. Hi, Caitlin. Caitlin and I were in grad school together, so this is very fun. So that's kind of what we're hoping to do with the like interactive dashboard that would tie into the database we're going to publish. Because we can't really. It's clear that when we talk to people like visiting in the watershed, that some groups, they're like, well, any information would be useful, but some people, like the ranges of interest and what people are particularly interested in is quite varied, and so there's no real way for us to address all of that in one go. And so we're hoping to be able to provide kind of the summarization tools or visualizations in that interactive web app so that people can hone in on their particular interests. And then kind of on top of that, because this is also, it's, as you saw in some of in kind of the methodological pieces of this work, there's just a lot of different modeling pieces to this, and it's going to produce a large ensemble of data. We're also hoping to, and this kind of gets to some kind of follow-on work that we're hoping to conduct. We're hoping to do kind of a curated look through the data set that might be a little more approachable, to kind of give people a sense of what they might find if they really wanted to dig into it. And that we're hoping to do that and to use that kind of along with our final sharing of the data.
Thanks for that. And please, if you have follow-up thoughts, questions to your question, please feel free to jump in again. We have a comment from Kenneth about the usefulness of your work to the fishery management, and so I'll let folks read that comment in the chat. Asmal, do you have another question?
Yeah, if time permits.
Yeah, go ahead. Maybe make it a quick one.
Hi, Theo. Thanks again. I have questions. I know Tongu River is located in the Missouri River Basin. So it is indirectly connected with the river basin, major river basin through Yellowstone River, as you mentioned. And there are studies based on the climate change model scenario, a simulation are proposing that Missouri River Basin is going through a hydroclimate puzzle, arguing that despite all the concerns and projections for drought, the stream flow in the Missouri River is increased in the recent climate as compared to the previous climate. Do you think that it has any implications, directly or indirectly, on the stream flow of the Tonga River?
Um, I don't want to speculate too deeply because um, we haven't completed the full suite of the modeling yet, and but I think what I showed in those just kind of climate contextualization slides might kind of get at this, and that um, particularly in the headwaters, there's definitely the winter and spring seasons appear to be getting wetter, and the fall seems about the same, and the summer looks a bit drier, and how all of that interplays with the warming temperatures that those plots showed as well. I think can get at how the some places might see increases in stream flow and some places might see decreases. Um, and I guess I'm familiar with some of the work that you mentioned. Like there's these kind of mesoscale circulation patterns that come across the interior of the U.S. that can drop a lot of precipitation, and those have implications for flooding patterns and things like that. Um, I could and this is going to depend on how the rest of the modeling work shakes out, but you could see some buffering of any potential streamflow losses because of these increases in precipitation. But I think that's also why the timing of flow is particularly important to consider as well, because that might affect reservoir operations, and when we might that might cause a mismatch between when water is available and when people actually can use it on the land. Um, yeah.
I just want to also qualify that, or clarify that, I think if you look at the whole of the basin, we see an increase in the flow, but really most of it's probably coming out from the eastern part of the basin in the plains. I think the headwaters on the west are showing generally a decreasing trend in recent times. So there's definitely, yeah, a divergence in kind of where you're looking at across the basin.
Thank you.
I think we're running out. We've just run out of time at this point for formal questions. At this point, I will stop recording, and we'll thank our speaker for his time and his presentation, and then we'll transition into an informal session. And please stay on if you want and ask more questions in a more informal setting. Thanks again to you.
Yeah, thank you all for the opportunity to share this and to discuss some of the work.